Hi, this is Module 2, Lesson 7, Linear and Exponential Functions. So this is the practice problems. I'm going to go over some of them, not every single one, because some of this should be review. I'll start with this first page. Evaluate the functions and creating tables of values. We're going to fill in the table of values for each function, then look for patterns and connections in your work. So to start with, we'll go ahead and fill in number 1. So what they're saying in here is I'm going to substitute each of these numbers in for x and then put the answer over here. So 3 times -1 plus 5 would be -3 plus 5 would be 2. So a 2 would go in there. 3 times 0 plus 5 would be 5. 3 times 1 plus 5 would be 3 plus 5, which is 8. And I have small boxes for me. 3 times 2 plus 5 is 6 plus 5, which is 11. And 3 times 3 plus 5 is 9 plus 5, which is 14. So this side is filled in. Make that 8 just a little nicer. That bothers me. 8. All right, so then now we're going to do it on this one. So notice the difference between these. This is 3x plus 5. This is 3 times x minus 1 plus 5. So very similar. Let's see how it affects their answers. So here I'm going to put a -1 in here. So -1 minus 1 is 3 times -2 plus 5. And that's -6 plus 5 is -1. Now I'm going to put in the 0, and so 0 minus 1 is 3 times -1 plus 5. Notice now I'm back over to what I did over here, and that was a 2. If I plug in the 1, so let me erase this and put in a 1 up here. 1 minus 1 is 0, so 3 times 0 plus 5. Oh, that's the same as this one over here. And so that is now a 5. So notice my numbers are very similar. I'm going to keep going. Notice my numbers are very similar. They're just off by 1. 8's down here, 8's over here. 11's here, 11's over here. So that -1 basically drops us 1 level from what the original. So that's what you're doing on these. I'm not going to work on the others. Basically, you can plug them in and just see the difference between an x minus 2 and an x plus 1. 2 to the x, 2 to the x minus 1. 2 to the x minus 2, 2 to the x plus 1. Notice it's the same things as above. There's now their exponents. So that's what they're trying to see, get you to notice, is just tweaking that equation a little bit, how that affects the rest, the results you're getting on here. So that's the first page. The second page is the main one I want to focus on. So this is what we talked about in the lesson, was how to convert these back and forth. Now, some of these are simplified, some of them are not. We want to go back and forth from radical notation, so that's with our roots, or rational exponents, and that's with the fraction as the exponent. So we want to rewrite each of the given expressions in the missing form. So sometimes it's radical, sometimes it's exponential, and then express in the most simplified form. So first of all, when I'm doing this, we remember that this is my denominator. Whatever the root is my denominator. And whatever the exponent is my numerator. So when I go to put it on this side, I have a 5, because that's my base. and I'm going to put it to the 2 over 3 power. My root is the third root, second power, third root. Okay, I'm not going to color code all of these, but that's what we're looking at. So I'm going to go ahead and do the next one. We'll do them in green right now. So 16 is my base, so I know that's going to go under my root. And my denominator is 4. So this is my fourth root. And my numerator is 3, so that's my power. So I have the fourth root of 16 to the third is the same thing as 16 to the third fourth, 3/4 power. So now here I've got two different numbers. So I'm actually going to just kind of split it down the middle, and we're going to do each one separately. So first I'm going to look at the 5. So let's do 5 to the 7/3 power, because that's 7th exponent, root is third, times, now let's do my second one, 3, his exponent is 5, and it's still over 3. So there's still the third root. So my root here should show up as my denominator for both of them over here. That's one way I can check to see if I've done this correctly. All right, let's go to this one. So now we're going to reverse that. Notice my denominator is 3 for both of them. So I'm going to go ahead and put this as a third root. And I know I have 9 to the, can't read it now that I put that mark on there, 2/3. So squared, and it's times 9 to the 4th. Well, I can actually simplify this because there's both the same bases. So I can do cubed root of 9 to the 6th. When I multiply bases, I'm adding my exponents. Well, third root of 9 to the 6th, 6 divided by 3 is actually 2. So my final answer would be 9 squared. That would be completely simplified. All right, let's look at this one. Let's split it down, go one of each. So they're the fifth root, so I know that's my denominator. I want x, power is 13, root is 5, times y, power is 21, root is 5. Make that a little bit more readable. There we go. All right, and that's all the further we can go. Yes, they're improper, but at this point, that's what we're going to do with it. Okay, scroll down a little bit. This one, we start getting a little more complicated. So now I'm going to have 3 different numbers or variables with there that I'm going to split. So I want the, oh, I don't need a root sign, I need the exponent. So 27 to the 1/3 power, because notice there's no exponent. There's no exponent up here, so the assumption is that it is a 1. A to the 5th, so times a to the 5/3 times b, exponents 2, we're still the third root. So notice I have a 3 as my denominator for all 3 of them, and it's all the third root. Now I can actually simplify this one more time, because 27 to the 1/3 power reduces to 3. The cubed root of 27 is 3. So I can put just a 3 times a to the 5/3 times b to the 2/3. And now that one's simplified. All right, next one. Looks a little uglier. No panicking though. We'll take them one at a time this way. So we have a numerator and a denominator. Here we have 32 to the 1/5 power, because we have a, why it's not writing for me, fifth power. And then we're going to take our x times x to the 13 fifths power. Now let's go to our denominator, 243 to the 1/5 power, and then y to the 15 fifths power. A lot of numbers there. We can't reduce it though. So 32 to the 1/5 power. Well, the fifth root of 32 is actually 2. 13 fifths doesn't reduce evenly, so I'm just going to leave that as x to the 13 fifths. Let's look at our denominator here. 243 to the 1/5 power. So the fifth root of 243 is actually 3. And if I look at this one right here, 15 divided by 3 is a whole number of 3. So I can actually simplify 3 of the 4 numbers in here and get a final answer of 2x to the 13 over 5 power over 3y to the third. All right, last one. Let's turn this guy into a root. If I look here, I've got 2 different roots. Here I have a 2, here I have a 3, here I have a 2. So I need a square root and a cubed root. So I'm actually going to erase those so I can see my numbers easier. So under the square root, I'm going to put the 9 to the third times the other square root one, t to the half. Oh, sorry, it wouldn't be to a half, just the square root of t. So because it's a 1, I just have t to the first. Times, now I'm going to throw in this one, cubed root of s to the 6th. Now, if I look at simplifying any of these, I can actually simplify 9, 3 is bigger than 2. And so because it's a square root, I can't actually simplify. I can say, well, 2 of those can come out to make a 9. And then I'm still going to have the square root of 9 and t, because this is 2 9s, 2 roots of 9, and there's the third root of 9, times 6 as an exponent. I need 3 of each of these to make a whole one. Well, I can get 2 sets out of there. So then it's s squared. So you could leave it like this, or you could do a final answer in a little bit more proper mode, would be 9s squared, square root of 9t. This would be the best final answer for that one. Okay, let's move on to the third page. So this is practicing drawing some graphs. So ideally, we want to get these into y equals mx plus b setup, because that's how we know where our x-intercepts are and the y-intercepts. So the x-intercept, in case you don't remember, is where it crosses, can't read that at all, crosses the x-axis. The y-intercept crosses the y-axis. So in other words, as we're filling these in, the x-intercept is going to be when y equals 0, because that's when it crosses the x-axis here. And the y-intercept is going to be when the x equals 0, because that's when it crosses our line up here. So let's go ahead and get this into y equals mx plus b. So we can distribute our 5 to get out the parentheses. So we have 5x minus 20, 5 times 4, minus 10. We can actually simplify those guys, the 20 and the 10, and say 5x minus 30. Well, we know when y equals mx plus b, our plus b here is our y-intercept. So negative 30 is our y-intercept. Now to find the x-intercept, I need to know when y equals 0. Well, y is my answer. So I'm going to write 0 equals, and then put my equation, 5x minus 30. And to undo that, I've got to add 30 to both sides. Those cancel, leaving me 30 equals 5x. To get rid of my 5, it's a multiplication, so the opposite is division. What you do to one side, you got to do the other. 6 equals x. So I know that my x-intercept is at 6. So now I've got to get these to fit on the graph. So I need negative 30 to be on my y's. So if I count kind of my different numbers here, I think if I go by 5s, I can make them fit. So this would be negative 10. This would be negative 20. This would be negative 30. So I'm counting by 5, 10, 15, 20. Label them on the top. Now, if you go by ones, you don't necessarily need to label these. Looks like a negative on there. Negative. But it never hurts to have labels, so no, there's no confusion. And then so for the x's, I just need to go to 6. So 1, 2, 3, 4, 5. I'm going to label this one at 5, 6. 1, 2, 3, 4, 5. Label this as negative 5. I like to label my axes. And so now I'm going to plot it. So 0, negative 30, 6, 0. I know those are that's my graph and my intercepts, so it must connect those. Okay, let's try one that's exponential. So over here, again, I want an x-intercept and I want a y-intercept. Well, let's start with the y-intercept because I can just plug in a 0 for this and get an answer for y. So if I plug in a 0, 5 times 2 to the 0, 0 minus 1. Oh my goodness. Get that out of here so I can see my work. There we go. To the 0 minus 1. That is the same thing as 5 times 2 to the negative 1, which is the same thing as 5 times 1, 2, 5 times 1 half, right? Because the negative puts the 2 as a denominator. So 5 times a half is 2.5. So I know my y-intercept is 2.5. Now to find my x, I have to put a 0 in for my x, or my y. So 0 equals 5 times 2 to the x minus 1. I start solving this. To get rid of that 5, I need to divide by 5. Those cancel. What I'm left with is 0 equals 2 to the x minus 1. Now, there's actually nothing I can take 2 to the power of to get me an answer of 0. So that actually tells me that there is no x-intercept. So this exponential equation is all above or below the x-axis. So now I have to determine where is it at on this this if I have to, if I can't cross the x-axis. So I know my y's need to go to 2.5. I'm actually going to go up by, I'll just go by ones. So 1, 2, 3, 4, 5 here. And I know at 2.5, I'm going to have my y-intercept. Do that in yellow. So let's do 1. Let's plug in a 1 for this so that we can see what we get if we're going to the right over here, if we're going to the left. So 5 times 2 to the 1 minus 1. We know 1 minus 1 is 0. 2 to the 0 is 1. 5 times 1 is 5. So my next point will be 1 comma 5. Okay, so now I know I'm going to go up this way in an exponential format, so it's going to be curved. And then to the left, I'm going to go close to 0 on the y's, but I'm never going to actually hit it. So I'm not going to cross the x-axis. All right, that's the only one we have for exponential. So let's try one of these guys. So let's start with what we know. X is, the y is a 0. The y is a, y-intercept is when an x is the 0. Oh, look, we have the distributing again. So let's go ahead and distribute that. It's a negative this time. Make sure you carry it with it. So negative 2x minus 6. Okay, y equals mx plus b form. So that means my x, when it's 0, my y-intercept is negative 6. So I can take this and go 1, 2, 3, 4, 5, negative 5, and I'll know my first dot is at negative 6. Okay, let's plug in our 0 for y. 0 equals negative 2x minus 6. First step, cancel out my minus 6 with the opposite, plus 6. That leaves on this side 6 equals negative 2x. To get rid of a times negative 2, I need to divide by negative 2. Those cancel. And x equals negative 3. So my x-intercept will be negative 3, which means I can just go by ones here. 1, 2, 3, 4, 5. Negative 5. My point will be at 0 when the y is 0 at negative 3. And again, it's linear, so I know if I connect those 2 points, this will be my line. All right, last one. Let's fill in these guys. X-intercept is when y is 0. Y-intercept is when x is 0. Hey, look at that. It's already in y equals mx plus b form. So I know my negative 8 is my y-intercept. And looking at the countings from my other graph, I need to go by 2's to get to negative 8. So 2, 4, 6, 8, 10. So here's a negative 10. And negative 8 will be right above it here. Okay, let's plug in our 0 for y. 0 equals 2x minus 8. Get rid of my minus 8 with the plus 8. Those cancel. 8 equals 2x. Get rid of a times 2 with the divide 2. And x equals 4. So my x-intercept will be 4. And I can count by ones. 1, 2, 3, 4, 5. And my dot will be at the 4. And now I've got my 2 points. I connect them, and I have my equations line. Thanks for joining us today, and we'll see you next time.